Alright everyone, today is the big day. We're going to talk about macros and symbolic execution. This is the defining feature of Clojure and the Lisp family of languages, so you're in for a real treat today. Alright, so as we saw in the previous video, when you define a variable, let's say you define x is 10, you can access the value of the variable, but you can also access something called the symbol of x, which is basically the name that's used to represent x in your code. And then if you want, you can actually go ahead and evaluate that symbol and get the value that's inside of the name x. Now we can get the symbol for all types of things in Lisp. We can get the symbol of a variable and even namespace it properly. We can also get the symbol corresponding to a function. So for example, if I define, let's say add 10, then I can get its symbolic representation and then evaluate it, and it works exactly the way you would expect. I can even get the symbol for public functions, for control flow statements like if and when, and I can even get the symbol for definition statements like def and for defn. So basically anything that you can use in the language, any sort of like thing that you could think of to type in Clojure, you can go ahead and get a symbol for it. Now, what's really interesting, and what we're going to spend most of our time talking about today, is what happens when you try to get the symbol of a full expression. So what happens when you try to get the symbol of a full expression, something like plus 3, 4. So this isn't just one individual symbol, it's a statement consisting of many symbols. All right, so what do you think is going to happen when I evaluate this? I get this result, which is actually the same as list plus 3, 4. And these expressions are exactly equal. And this is huge. It means that if you have an expression, the symbol for that expression is a list containing all of the symbols inside of that expression, which means that without doing any work at all, you already have access to your entire expression as a data structure. So let's go ahead and let's see what this means. So if I go ahead and I get the symbol for the expression plus 3, 4, remember that the symbol for this expression is actually a list of subsymbols, which means that we can do list operations on it. Like we can get the first element of this list, we could get the second element of this list, we can add stuff to this list, replace elements in it. Basically, all of the list operations that you would do in your code, you can do on your code itself. This is one of the reasons why Lisp is called list processing. Because when you evaluate an expression, what you're actually doing is you're evaluating a list of symbols, which are in turn themselves raw values or sublists of symbols. So now let's look at a more complicated expression. Let's say I have something like plus times 2, 3 times 4, 5. So this is an expression made up of two sub-expressions. If I get the first element in the list, it's plus, exactly what we would expect. But then if I get the second element in the list, it's the symbol for this expression right here. So second expression 1 is actually equal to the symbol of times 2, 3. Now you might notice here that this in itself is an expression. So this is represented as a list, and then I can do things like get the first element of it. And so in this way, a single expression is a list of symbols, and a nested expression is a list of lists of symbols. I could write this expression out fully as something like this, and it would be exactly the same. What this means here is that you have access to your entire program as a data structure by default, without doing any extra work. This here is a list of lists. So I have access to the entire program represented like a tree. So now let's do some stuff to it. Let's say I had an expression that looks like this, and I wanted to replace the second argument of every multiplication call with 2. So I want the output to look something like this. I could write a function, replace second arg, that takes a symbol expression as input. And now we're just going to recursively go through and replace all the operands. So if the symbol is not a list, i.e. it's an end node in our expression, then we don't want to do anything to it. So we just return the expression itself. Then if it is a list, but the first element is not equal to times, then we want to run replace second argument on all of the sub-expressions. So for example, for this top level expression, we want to run replace second arg on this, this, and this, and that's our recursive step. And then finally, if the first symbol is equal to times, then we want to set the second element of the list to 2. So the way that I'm doing this here is I'm first converting it to a vector so that I can set an element in the list, and then I'm converting it back to a list at the end. And then since some of the multiplies might have another multiply inside them, I also want to run replace second arg on every element in the result. Now if I go ahead and I run this and I take our expression as input, I get back the same code but with all of the second arguments of the multiply calls replaced by 2. And this is really special. We've created our first little program that takes code as input and produces code as output. Now, this isn't necessarily the cleanest way to write it. Clojure has some really nice libraries for walking down trees and kind of doing tree manipulation. But I wanted to do it this way just to show you how far you can get with just the basic operations and also to make it easier to understand for people who aren't as familiar with tree algorithms. All right, so now that we have all the basics down, it's time to start cooking. You're probably familiar with let statements, just to assign the value of a variable. A really common pattern in Clojure is to initialize a variable, and then if that variable is not nil, to proceed with the rest of the evaluation. So something sort of like this. So I want this type of behavior, but I don't want to have to write out all of this code every time. I can't really easily put it in a function because of the way it assigns a variable and also conditionally executes some code. But what I can do is figure out what the ideal syntax would look like, and then write a program that transforms the ideal syntax into code that actually works. So using our knowledge of everything that we've just discussed, let's see if we can sit down and actually do this. So first I'm going to define what does the ideal syntax look like. So when I'm writing code and I want this behavior, what I actually want to type is something like conditional let x is equal to do some request of input and then do some stuff of x. So basically I would want to type this, but then have the same behavior as what I have up here. So this would assign the value of x, and then if x is not nil, it would do some stuff over here. Now what's really cool here is this is the minimum information I need to specify as a programmer to actually get the behavior that I'm looking for, right? I have the name of the operation that I want to do, what variable I want to assign, and what I want to assign it to. And then finally, the conditional code that I want to evaluate, right? And so I have only the new behavior that I want to define. All right, so now let's see if we can write some code that transforms the ideal syntax into code that actually works. So we're gonna write a piece of code that transforms something that looks like this into something that looks like this. So the first thing I want to do is I want to grab the symbol representation of the ideal syntax. And then what do I want the output to look like? Well, I want the output to be a symbol expression. So I'm going to start with a list. Then the first symbol of that expression should be let, which is the same as this let right here. Then the second element of the symbol expression should be this statement right here, which is actually the same as this statement. So that's the second element of ideal syntax. And then the third element in the expression is this statement right here, which is itself an expression. So I'm going to make another list for that. Then the first element in this last expression is when. So I'm going to type when. Then the next element of this when clause is itself an expression. So I'm going to make another list for that. And then this is also an expression. So I'm going to make another list to hold that expression. And this expression is a list containing nil and the symbol x. Now the symbol x is defined here. So we need to grab the symbol x from inside of here. So that is the first element of the second element of ideal syntax. So the second element of ideal syntax is this. Oops, let me scroll down a little so it's easier for you to see. So the second element of ideal syntax is this. And then the first item of that is this. Also, this nil should have a question mark. So now we can see the first list we've defined here is nil question mark x. And the second list we've defined here is not of nil question mark x. So this whole piece right here is a whole bunch of nested symbol expressions, or S expressions for short, whose whole value is this symbol expression right here. Evaluates to not nil question mark x. So now we need to finish writing the rest of this when clause. So the first argument to this when clause is this not nil question mark x that we just wrote. And then the second argument to this when clause is do some stuff of x, which is actually this statement right here. So the second argument to this when clause should be nth of ideal syntax of 2. So now I can go ahead and evaluate this and get exactly the output I'm looking for. All right, so we did this with ideal syntax as an example variable, but let's just go ahead and just really quickly turn this into a function. So I can write defn conditional let transform of input symbol, and then just replace all the ideal syntaxes with input symbol. And then if I run conditional let transform on ideal syntax, I get the expected output. All right, so now if we had some code that actually looked like this and we wanted to use it just like when we were programming, it would be really annoying because first we would have to grab the symbol for the code, then apply the transformation, and then we would have to evaluate the resulting symbol. So this is a lot of work, and Clojure provides sort of an easy way to sort of do all of these steps automatically. So if I go ahead and if instead of writing defn to define a function here, I instead write def macro, then it will automatically quote all of the arguments, and then it will also evaluate the result after the transformation is done. And what's really important to note here is this piece of the expression, because we took its symbol before we did anything with it, is transformed before it is evaluated. And that's why we say this macro is executed at read time, because it happens during the process of reading and pre-processing the code before the final program is evaluated. Now, because a macro automatically quotes all of its arguments and turns them into symbols, we can actually make this bit of code even simpler. So instead of even needing conditional let transform, we could write def macro conditional let with its 2 arguments, the initialization block that gets passed to let, and the code to evaluate if the block is non-nil. Then we could return the same result that we came up with earlier, except just inputting the actual argument names where the arguments are used. So this would change to code to eval. Then if I go and I execute this, I can say conditional let x is 10. And then I want to return x is not null. And then just for completeness, if x is nil, then it doesn't print anything. So now let's just walk through this and take a closer look at what this code actually does. So this macro, conditional let, at read time, when the code is read in by the interpreter, it first takes in these 2 arguments and converts them into symbols. So this is a symbol that gets passed into init block, and this is a symbol that's its second argument, so it gets passed into code to eval. Then it applies this macro, conditional let, which takes these two inputs and returns this value as output, which is a symbol that looks like this bit of code right here. Then, before any code is actually evaluated, it swaps this bit of code with this symbol, and it evaluates the resulting symbol instead. So if I want to see what symbol it's actually evaluating, I can go ahead and I can type macro expand, and I can see that when I type this in my code, it's actually evaluating something that looks like this. Now your code might use lots of different macros, just like during the course of you programming. So if you want to just only expand the top level macro, you can type macro expand -1, and then it will only get the expansion for this macro, and it won't try to expand every possible macro that exists in your code. So this is it. We've created our first working macro and changed the syntax of the language. Now when I type conditional let, I'm using different syntax to create behavior that I've defined. And this is a really, really powerful tool. I want to emphasize that it would be impossible to get this kind of concise syntax just by using functions or lambda expressions, because the function evaluates all of its arguments before the function is called. So you couldn't do this kind of conditional evaluation. And this macro relies on the definition of the symbol x, which is not declared anywhere else in the code. Last up, before we close out, I just want to go through some practical considerations with writing macros and show you kind of the style to write them cleanly and efficiently. So one of the things you might notice is that different symbols might mean different things in different namespaces and different contexts. So for example, if I did something like let nil, so basically I say that nothing is ever nil, and I go and I evaluate this, it treats x as though it's not nil. So it uses this definition of nil rather than the canonical one. Even though it's rare for somebody to, locally create a variable that's called nil ? Most of the time when I'm writing code, I want this macro to work the same way regardless of the namespace or the environment that I'm running it in. So I want this to use the canonical definition of nil rather than, whatever it's locally set to. And so the way that I would do this is, instead of using a single quote, Clojure has this special syntax that's called a backtick that's specially used usually for writing macros that automatically resolves the namespaces of all of the symbols that are used inside of a macro definition. So if I write backtick nil ? You can see that it correctly resolves the namespace inside of clojure.core. Whereas if I just write single quote nil, then it doesn't do any namespace resolution. But this backtick syntax actually does even more than that. So if I put a backtick in front of an expression, it will namespace all of the symbols inside of that expression. So even if I had a nested expression like this. But what's really special about the backtick is that you can actually escape out of it. So if I go in here and I put a little tilde in front of just this part of the expression, and I go and I evaluate this, it grabs the symbol for this entire expression, but it escapes out and it evaluates just this bit of code. So this block right here is actually equivalent to list plus 3, 8. And so if I have a big expression, I can escape out of just specific parts of the expression and evaluate them by using this backtick along with this tilde. This is really, really useful because it means that we don't have to manually build up each of these individual lists when we're building a response symbol. Instead of creating each of the symbols at the token level, we can symbolize our entire list and then escape out only the parts that we need. So now let's rewrite our existing macro using this new backtick syntax. So I could do def macro, conditional let, init block, and code to eval. And then I'm going to use this backtick, and I want to return let and then I want to escape the init block because I want to return the value that's inside of this symbol, not the name init block itself. And then I want to do when not nil. And then I want to get the value inside of the first element of init block. So I'm going to escape that because I want this to be evaluated and grab first of init block. And then last up, I want to put in the code to eval. And then I can see that this works exactly the same way. And it also handles our let statement correctly. So I'm just going to macro expand this to show you what it's doing. And then I also want to show you the difference between escaping code to eval and not escaping it. So if I write the same expression, but I don't escape out of code to eval, so I don't evaluate this, and then I just return the symbol that's here, then if I go and I macro expand this, I can see that it returns test project.code to eval in my result. So it returns the symbol code to eval. I'm just going to change it back again to show you, rather than the content of what the argument is. So you can see here it correctly uses the input argument hi inside of the resulting expression. All right, so we did it. We successfully created our own Clojure macro. Now there's even better ways to write this than the way that I just did it here. Clojure actually has a built-in macro when let, which does exactly the same thing. But I think actually part of the big power of macros is that there are some very well-written libraries and some very well-written macros that are available for use. So even if you don't spend all day writing macros and thinking about this stuff, you can still get the benefit of having the ability to do so around in the language. Anyway, thanks so much for watching. Go forth and conquer. I have a really exciting Emacs video that I've been working on for about a month. So I'm really excited to show you guys that project in my next video. But after that, I'm planning to make a few more videos about Lisp and macros. I really want to make a tutorial in which we build our own object system starting from scratch using Lisp macros. So that's something that's really exciting to possibly look forward to. Anyway, if you made it this far, give the video a like, subscribe to the channel, and I'll see you in the next one.